So my interest in privacy arose in conversations with Helen Nissenbaum, a philosopher who specializes in problems that arise in the context of new technologies. So for the purposes of this talk, we're going to focus on a database that's full of all kinds of really useful but possibly sensitive information. And we'll have a data analyst that interacts with the database in a rather formal fashion. She issues what we'll call queries and gets answers. Depending on the outcome of the first query, she can choose a second query and get another answer and so on. So it's a completely adaptive setting. The census data was an original motivating scenario because census data privacy is legally mandated. But there are lots of other applications from epidemic detection based on over-the-counter drug purchases to analysis of loan application data for evidence of discrimination, and you can come up with many, many others. This is a really old problem with a literature that dates back at least 50 years to Warner's work on randomized response, which we'll discuss later. So you might try to say, we haven't said what privacy is, but what we want is that if we have a data set that is sort of a good, properly sampled sample from the general population, that when we ask questions of this data, we learn about the population as a whole without compromising any of the privacy of the individuals who are in the data set. So you might think that you can achieve this by restricting attention to just statistical queries. Now, I haven't said what statistical queries are either, but you probably have some kind of intuition. Right, your intuition is that the statistic is, in fact, giving you some understanding of the underlying population. That's why statisticians do their stuff. And you also have the intuition that the data of any one individual shouldn't really affect the outcome of the statistical analysis too much. Again, that's why statistics is supposed to work. It's not supposed to be about any single individual. It's supposed to talk to you about the population as a whole. So suppose we were able to formalize this and say, okay, the analyst can just ask statistical queries. So your intuition.
Just statistic, but just in the legally.
Right. So I call this the Statistics Masquerade. And intuition is just completely wrong here. So here are a few examples. The first is the differencing attack. So suppose we ask how many members of the House of Representatives have the sickle cell trait. So your intuition is that if you get the answer to that question, you really don't know anything about the status of any individual in the House of Representatives. Just an intuition. But suppose we also give you the answer to a second question, exact answer to a second question, which is how many members of the House of Representatives other than the Speaker of the House have the sickle cell trait. So if you have the exact answers to both of these questions, you can, of course, determine the sickle cell status of the Speaker. So it's not private at all. There are also other kinds of attacks, a sort of needle in a haystack attack that allows the possibility of determining the presence of an individual's genomic data in a genome-wide association study case group based only on aggregate statistics about the proteins in the DNA of the various people in the case group. And there are these big bang attacks, also known as Denor-Nisim attacks, which show that given statistics for multiple overlapping large subsets of the population, you can actually reconstruct sensitive attributes for everybody in the population. So these lead to a sort of fundamental law of information recovery, which says that overly accurate answers for too many statistics or estimates of too many statistics is blatantly non-private. And there are many instantiations of this particular fundamental law. We won't have a chance to go into them now. But it's a lot worse than that. And it's worse than that because statistics that are produced or actions that are taken based on analysis of data and that are observable in public take place in a network world where information flows and combines in mysterious ways. And every one of these pictures indicates a real story, either from the literature or from actual real life attack. So we're not doing things in vitro. Things are happening in vivo, and it's a really wild, wild west out there. So LaTanya Sweeney, when she was CTO of the Federal Trade Commission, advocating, in fact, for differential privacy, put it this way: computer science got us into this mess. Can computer science get us out of it? So you guys are cryptographers, and you know that among and enabling the tremendous advances of modern cryptography is a focus on definitions. So we're going to try to define now what we want to mean by privacy. What do we mean by privacy-preserving data analysis? So here we have this database, and Helen is in the database. What kind of privacy or protection is it that we would like to offer to Helen? So the first thing that you might try is that we shouldn't be able to learn anything new about Helen. That is, the analyst might know a lot about Helen to begin with. That's called auxiliary information. But by interacting with the database, the analyst shouldn't learn anything new that she didn't already know. And not only is this sort of the analog of semantic security for a cryptosystem, but it was also proposed 5 years before the definition of semantic security by the statistician Tordelinius for what he envisioned for a statistical database. The problem with this definition is that if we satisfy it, then what is the point of our statistical database? So to illustrate this, suppose I'm from Mars, and I incorrectly believe that all humans have 2 left feet. So in particular, I believe that Helen has 2 left feet. And I interact with the data set, and I learn that the vast majority of people have 1 left foot and 1 right foot. So now my beliefs about Helen have changed. And the question is, has her privacy been compromised? And this is a judgment call. We chose to say no, to say that this is not a privacy compromise. And the justification for this is that the same thing would have happened if Helen had been replaced in the data set by another random member of the population. In which case, we're sort of justified in a view that the database isn't leaking something specifically about Helen, but rather about the population as a whole. This is also known as stability, and we will come back to that. But learning the same things when you perturb the data set slightly is a very useful property to have. So this brings us to the English language definition of differential privacy, which says that the outcome of any statistical analysis is essentially equally likely, independent of whether any individual joins or refrains from joining the data set. So we'll learn the same things with very similar probabilities. If Helen goes away, LaTanya joins, Helen's replaced by LaTanya, and other small perturbations in the data set. Clearly, if we completely change the data set, we may get totally different answers. Like if we replace all the men by women, we'll get some very different answers. And that's to be expected. That's what we want. That's utility. But small changes shouldn't change things very much. Now, as you'll see, differential privacy is an extremely strong definition of privacy. It's very, very demanding. And so let me give you a little bit of intuition as to why we could still do something useful and actually get some meaningful data analysis even if we maintain this strong definition. And the key to that is that stability is known to yield generalizability, and in fact be required for generalizability. You want that the things you learn from the data set, you should apply to the population as a whole, and they shouldn't just be overfit to your data. That's called generalizability, and that's strongly connected to stability. Yes, what's your question?
How do you define a small change?
Don't worry, it'll come. So the key point here is that privacy and generalizability are aligned. And while you'll often hear about a tension between privacy and utility, here's a sense in which privacy and utility, learning about the population as a whole, are in fact aligned, and they are not in tension. So here's the formal definition of differential privacy, and this answers your question. First, I have to tell you what is a pair of adjacent data sets. So we say that a pair of data sets X and Y are adjacent if one of them is contained in the other, and the larger one contains the data of just one more person. So the whole data set versus the whole data set minus Helen. The whole data set versus the whole data set plus a new member, Latanya. Those are adjacent data sets. So our algorithms are going to be randomized. They're going to take a data set as an input, and they're going to chomp on it, and they're going to have some random bits. And so when the data set is X, M of X will be a probability distribution on outputs, and similarly for M of Y. Finally, an event is just a subset of the range of the mechanism, the algorithm. For some reason, the algorithms are always called mechanisms. So now we have everything we need to give the definition. We say that a mechanism or algorithm M gives epsilon differential privacy if for every pair of adjacent data sets X and Y, and every event X, the probability S, the probability that we observe S when the database is X, is close to, within an e to the epsilon factor, times the probability that we observe this event when the data set is Y. And notice that in the definition, the role of X and Y are completely symmetric, so we can flip them. And so we would have the probability of M of Y is in S is at most e to the epsilon times the probability of M of X is in S as well. And the probability space is over the randomness of the algorithm, not over the choice of the data set. So it's a worst case guarantee because it's guaranteed for every pair of data sets. It has absolutely nothing to do with who happens to know what. This is just a statement about the behavior of an algorithm. It doesn't care what somebody interacting with the algorithm or calling the algorithm happens to know or not know. And since this is the randomness of the algorithm, and the algorithm we're always going to assume is run by a trusted and trustworthy curator, the randomness is in the hands of the good guys. We control it. So that's very important. And informally for now, I'm going to describe, I'm going to call epsilon the privacy loss. Okay. Now there are a few properties. Yes?
Seems very related to statistical distance, right? So how does this definition compare to saying that statistical distance between M of X and M of Y is small?
There is a relationship. It's close. Yeah. Yeah.
You had the English
Yes.
formulation.
Uh-huh.
Did that formulation exist before the
No, that formulation did not exist.
natural one that people could have thought about before?
Right.
No one formulated it that way.
No, that's correct. So it's new. So let me describe some properties that flow from the definition, not from any particular implementation. First of all, if an algorithm is differentially private, it's differentially private no matter what anybody happens to know. I made this point earlier. So in fact, it's immune not only to all auxiliary information right now, but it's immune to any auxiliary information that the adversary might learn 3 years from now, thinking back over all of science that has evolved in the last 3 years and the answers that were received today. If an algorithm is epsilon differentially private, then it is automatically k epsilon differentially private for a set of size k. So smaller epsilon is better privacy, k epsilon is bigger than epsilon, but nonetheless there is some natural group privacy. We can understand and analyze the cumulative privacy loss over multiple analyses, and very rigorously. In the worst case, the epsilons add up.
What is the typical case? What is the typical case? In the worst case, they add up. Can you say something?
I will later. I prefer to wait. From composition, we get the most important property, which is programmability. So what it says is, if you understand a few simple differentially private primitives, you can now combine these primitives in interesting and creative ways to find privacy-preserving methods for more complicated analytical tasks. So we're in a situation that's a lot like you have with algorithms in general. We know how to add, and we know how to multiply, and all of algorithms is the question of combining these abilities of adding and multiplying in creative and interesting ways in order to optimize various kinds of costs, such as time and number of random bits and space and things like that. So in differential privacy, we want to do those same sort of things, but we want also to minimize one more thing, and that is cumulative privacy loss. So this is where all of the power of differential privacy comes from, and there's nothing else that has this kind of power for private data analysis. So let's look at a couple of ways of achieving differential privacy, some of those simple computational building blocks. So here's something that's none of my business. And you probably have heard of this approach. This is due to Warner, 1965. So I want to ask this question, but of course you're not going to tell me the answer directly. What you're going to do is flip a coin. And if it's heads, you're going to answer randomly. That is, you'll flip a second coin and respond yes if heads and no otherwise. And if it's tails, you're going to answer me honestly. So this is, with a slight change to the definition, this is differentially private. And you can analyze in a really easy way what is the parameter epsilon that you get. So it's not hard to see that the probability that you say yes, given that the truth is yes, divided by the probability that you say yes, given that the truth is no, is a third. And similarly, for answers of no. So what that tells us is that this log ratio is the natural log of 3, which is 1.098 roughly. So statisticians are very familiar with that. And if you're interested in the question of how many people in the data set XYZ last night, you can estimate that because you understand the random noise and you can sort of factor that out. And what you'll end up with is an absolute error that's tightly concentrated around square root of n. So things cancel out nicely. And you'll be able to, right, fine. And sometimes we talk about fractional error So we're asking not how many people in the data set, but what fraction of the people in the data set. And so the fractional one will be an answer between 0 and 1. And fractional error here looks like 1 over root n. Here's a second general approach. I should mention that randomized response is actually being deployed by Google to estimate the prevalence of malware in the Chrome browser. And they're using the properties of differential privacy to analyze cumulative privacy loss. Okay, so suppose we want to look at getting estimates of real valued functions. So here's a data set, and we're interested in some function f of the data set x, and this star is f of x. Now, remember that we need to sort of blur the difference between when the data set is x and when the data set is any neighboring y. So here's a neighboring data set y. It has one more point in it, and f of y is now this yellow star instead of the red star. So we want to add some noise that will obscure the difference between f of x and f of y. So maybe we'll have this be the probability distribution on outputs when the data set is x, and this will be the probability distribution on outputs when the data set is y. And what we need is that at all points here, these two guys satisfy that ratio of e to the epsilon, that the ratio is always between e to the minus epsilon and e to the plus epsilon. What this suggests is that, So let's let delta f, which is called the sensitivity of the function f, denote the maximum over all pairs of adjacent data sets x and y of the absolute value of f of x minus f of y. So this is how much, what magnitude the noise has to cover or has to obscure. So informally, the theorem statement is going to be that to achieve epsilon differential privacy, it suffices to add symmetric noise that is scaled to this quantity. So let's talk about this quantity for a minute. By scaled to, think sort of standard deviation, roughly. That's how big you expect it to be. First of all, the noise depends on the function f and on epsilon, but not in any way on the data set, nor on the size of the data set. So if we have a function that is sort of monotonically growing in the size of the data set, things like counting queries, how many people in the data set are over 6 feet tall, for example. This is something that's growing with n, but the noise distribution is fixed and independent of n. So when n gets large enough, the noise is completely tiny compared to the answer. So we can, okay. Now, something about this form. If my presence or absence can radically change the value of the function, we're going to have to add more noise, bigger noise, to hide my presence or absence. So here's delta f in the numerator, where it belongs. Now, a smaller epsilon is better privacy. And if you want a lot of privacy, then you kind of have to broaden the distribution, make it a wide standard deviation. And if you don't care so much about privacy, it can be smaller. So here's epsilon in the denominator, where it belongs. When epsilon is small, this blows up. So everything has the right form. Moreover, because of the fact that the noise sort of stays fixed, but the size of the database and therefore the value of f could grow, we tend to think about this as privacy in the land of plenty. When data are plentiful, this gives good answers. If the data set is very tiny, the true answer will be completely obscured by noise. That's just true. So differential privacy is not a tool to use on tiny data sets. So here's the exact distribution that we like. It's the Laplace distribution. So the parameter is b, and this is the density function. So the density function is dropping off exponentially in z divided by the parameter. And the standard deviation is roughly the parameter. So increasing the parameter will flatten the curve, give you better privacy. The same argument actually will work, and I'll give you the argument in a minute, for vector-valued functions. So there was nothing really, really special about the fact that I was looking at real-valued function. Here we just have to redefine sensitivity to, instead of being just an absolute value here, it's a one norm, which is the sum of the absolute values in each of the coordinates. So what you would do is you compute the sensitivity and you add noise scaled to the sensitivity over epsilon, independently drawn for every coordinate of the output. And the same thing will also work if we want the answers to many functions. We can just think of the many functions as giving us a vector, and we can look at the sensitivity of this string of functions. Okay, so why does it work? So we'll use shorthand here for the density function of m of x at t. So we're interested for two adjacent data sets in this ratio. And plugging in what we had for the density function, we have t minus f of x divided by the parameter in the numerator, and t minus f of y divided by the parameter in the exponent in the denominator. So when you put those together and we apply the triangle inequality, we get here something that's at most the one norm of f of x minus f of y, which of course is bounded by delta f by definition. And the delta f's cancel, and we get exponential and epsilon. So here's the first application that I know of that really told me something was happening. Adam Smith told me this application, and it really got my attention. So, histogram query. A lot of statistics have the following form. You have your space of people, your universe of possible people. You carve the universe up into disjoint chunks. For example, people with annual income between 0 and 25,000. People with annual income between a little more than 25,000 and 50,000. A little more than 50 and 75. Those are disjoint chunks of the universe of what people's annual income could be. And you want to know for each chunk how many people are in that chunk. The standard histogram query. So you could view this as a large collection of counting queries, one for each chunk, and you could say, okay, this is a high-dimensional query. But if you think about a histogram, if you add or delete one person, you will only change the count in one cell, and you'll only change that count by at most one. And so the sensitivity of the query is just 1. And so it's enough to add noise that's scaled to 1 over epsilon in each of these different cells and release the result.
Maybe it doesn't matter because you could be changing the count in your example in 2 cells?
Sorry?
Maybe it doesn't matter, but wouldn't you be changing the count in 2 cells?
No, because we're just adding a person, and that person can only live in one possible cell.
You're not
But
moving.
he's moving to another, he's now earning 30,000.
I defined adjacent data sets as one is a subset of the other, and the data has the data of just one more person. You're absolutely right, and sometimes it's very helpful to think of adjacency as what happens if you move somebody around, and then you get the factor of 2. Well, we also want to do some kind of an accuracy analysis. I've told you about privacy, but what about accuracy? So this is the kind of result that we can get, and I'll show you how in a second. Suppose you want to know which from a set of 10,000 first names were the most popular in the 2010 census. Okay, So this is like a histogram query with 10,000 cells. So if we take epsilon to be 1, then we can argue that with probability 0.0595, no estimate will err by more than about 12. So for this, we have to introduce a notion of alpha-beta accuracy, which is the following. A mechanism is alpha-beta accurate with respect to a set of queries Q, if for all databases X, with probability at least 1 minus beta, the output M of X permits the analyst to compute an approximation that's within alpha of truth for every query. Okay? So whenever I talk about alpha-beta accuracy, I'm always talking about with respect to all of the queries in the set simultaneously. All right, so we're asking what accuracy does the Laplace mechanism provide for k-counting queries. Counting queries are going to be our running example. So with k queries, we're going to have the sensitivity, the sensitivity for k queries, k counting queries, is in general k, because adding one person might, say, increase the counts for all of the k queries. And so the L1 norm of the difference of the counts on f of x and on f of y will be k. So we're going to add noise that's drawn from parameter k over epsilon. And we're going to use this fact about the Laplace distribution, that the probability that we exceed t times the parameter is at most e to the minus t. So we're going to, yes?
This alpha-beta accuracy definition is just saying that M is a pack, and this is how good of a pack it is. Is that fair to say? I guess it's an additive error.
It's an additive error. Okay, so we're just going to, look at the probability of exceeding our parameter by a factor of t, and we're going to apply a union bound and our fact. So we get that k over beta would be e to the t, so t is ln k over beta, and we get that alpha is k over epsilon times the log of k over beta. Okay, so for the Laplace mechanism, this is our privacy guarantee, accuracy guarantee. So let's look at the case where k is 1, just a single counting query. In randomized response, we had an error of root n. Here, we're going to have an error of 1 over epsilon. So it's better. Epsilon is typically, we think of epsilon as a small constant. And we get something that's at least potentially sensible as long as we don't ask n queries. We get some non-trivial accuracy for almost up to n queries. Here's another trick, another little toy. Suppose we have a bunch of functions, and we want to know which function achieves the maximum value on this set. So, for example, g1 of x might be how many people like ping pong. g2 of x might be how many people like to eat muffin tops. G3 of x can be how many people in the data set go running regularly, and so on. So one person can affect many different of these things. But you might want to know simply what is the most popular hobby of these hobbies. So in general, for general functions, so one thing that you could do, of course, is add noise that is scaled to the sensitivity of the vector that you would get. G1, G2, and so on and so forth, but obviously that's not what we want to do. And what we are going to do is we're going to add noise that's scaled to the maximum sensitivity of any single one of these, but do not release the outcome. Do this computation still inside the curator, and report only the index of the function that has the largest noisy max. Hence the name report noisy ArgMax. That will tell you which of these things is well, it certainly tells you which is the largest noisy value, and if there's a gap between the true largest value and the second largest value, you're very likely to get the truly largest value. If the first and second, and you can extend that, of course, are fairly close, then who knows what you'll get as an outcome. The key point is you don't reveal any noisy values, except any noisy values at all. And the proof of differential privacy is by straightforward case analysis. So this is an example of a minimization principle. We compute much more than we actually release, and by doing so, we're able to get by with less distortion. Here's a tremendously powerful generalization of report noisy ArgMax. Oh, and of course, what I said also applies to ArgMin. All right, this is going to apply to very general notions of utility. So we've been talking about L1 error when we were just adding noise to real valued functions, but we might look at L2 error, or maybe we have a differentially private algorithm that's producing some kind of a classifier, and our notion of utility is smallness of classification error. So minus classification error. And in general, we want to use this when adding noise makes no sense. So one way in which adding noise makes no sense is if you say, which is the most popular hobby, it doesn't make sense to add noise to the answer table tennis. Just not meaningful. And in particular, it might be the case that what you're computing is a price for an auction. And if you add noise, in particular, if you add positive noise to it, you might suddenly price yourself out of having any buyers at all. So the general goal will be to maximize some arbitrary utility function. Sorry. This should not be y. This should be the value xi, which is what it'll look like just about everywhere else. So we have, and that should be a capital xi. So we're looking at functions whose outputs are some objects. They could be strings, they could be experts, they could be small databases, they could be prices. And each of these things has a utility for x, which we denote utility of xi on x. And the intuition here is that we will output the element xi with a probability that is proportional to e to something. So what do we have in the exponent? We have the utility, how good is xi as an answer for x, times epsilon divided by delta u. So this epsilon over delta u should have a familiar feel to you. You've seen this before. It's the inverse of delta f over epsilon. And the intuition for why this works is the following. Let's look at two neighboring databases, x and y. So when the database is x, we'll output xi with probability that looks like e to the utility of x, of xi for x, to this power. And when the database is y, we'll output xi with this probability to the same power. Delta u is the sensitivity of the utility function. It says, how much does the utility change if I change the database by one element? So delta u bounds this difference. And so this guy is bounded by delta u, and this is delta u, and they cancel, and we get epsilon. And formally, this mechanism, called the exponential mechanism, due to McSherry and Talwar, does just what I told you, although there's a normalization factor, and because of that, we get an extra factor of 2 up here in the exponent. Now, similar to the proof of alpha-beta accuracy, we want to prove something about how good is the exponential mechanism. And by the way, a little bit of thought will show you that the Laplace mechanism is the exponential mechanism on reals. So we're going to have a very similar looking proof. So if this is the set of possible outputs, and xi star is the set of optimal utility outputs, those whose utility is no worse than any other, then my claim is that for all values v, the probability that the utility on what is produced here when the database is x is bounded by v is at most this quantity. So what is this quantity? In the numerator, we see that if the utility of psi is bounded by v, then the unnormalized weight of psi is at most this, by definition of the mechanism, and there are at most psi many elements of that form. And then if psi star is the set of optimal elements, they have unnormalized weight e to the u star by definition. So their total unnormalized weight, is e to the epsilon u star over 2 delta u. So the normalization term here is at least psi star times e to the u star over 2 delta u. And then you just do the arithmetic and the exponents, and we get v minus u star. So the probability that we have utility at most v is bounded by this over that. Okay, so I want to make an historical note about this. Perhaps the motivating scenario for McSherry and Talwar was unlimited supply auctions. So in these auctions, bidders have demand curves that describe for every possible price in a fixed interval the number of goods that they want to purchase if the price is P. And let's say that each of them has a total budget of 1. So the auctioneer can choose a price that will optimize revenue. So the price, the revenue would be P times the sum over how much he's getting from each of the different bidders. And McSherry and Talwar's idea was that you should select the price using the exponential mechanism, where you define the utility of a price to simply be the revenue. And if you do this, you get an auction that's approximately truthful in the sense that an individual can't substantially change the outcome by changing her bid. Why? Because the exponential mechanism is differentially private. So you expect roughly the same answers no matter how somebody changes her bid. As a byproduct, they also got collusion resistance. That is to say, remember that if something is epsilon differentially private, it's k epsilon differentially private for a group of size k. So if you have a small number of colluding bidders, they can't have much of an impact on the price that's chosen or the distribution on prices that are chosen. And to my knowledge, this is the first instance of differential privacy providing a new result on a problem that has nothing to do with privacy. In other words, collusion-resistant auctions of this type.
Is this connection more general, the connection between differentially private mechanisms and approximately truthful? So the idea of approximate truthfulness or differential privacy as a solution concept has in fact been very fruitful. Yes, and there are several works that develop that and also the connection in general to economics. Here is an absolutely radical application of the exponential mechanism, which totally changed my understanding of what we could possibly hope for in differential privacy. So this is going to be a mechanism that will answer hugely many counting queries. So we're given an n-row database and a collection queue of counting queries. And the goal is going to be to produce a synthetic database, Xi, that gives a good approximation to the answers to the questions, what fraction of the rows of the original database satisfy property P for every property P in our set?
So what do I mean by a synthetic database? So I'm assuming that the database is a collection of rows where each row is drawn from a universe of elements. A synthetic database also has rows that are drawn from the same universe of elements. Those rows might or might not intersect with the original database. But what's desired is that the answers to the counting queries should be approximately the same. The fractional counting queries should be approximately the same. So our output space for the exponential mechanism is going to be the set of all small databases. I'll tell you what small is in a moment. We need a utility function. And the utility of a small database psi for x is the maximum fractional difference of q of x versus q of psi. So it's telling you what's the worst case error for among the queries in that set q for this thing. And the sensitivity of this utility function is just 1 over n. If I have an n element database and I take something out, I'm going to change the utility by at most 1 over n. These are fractional counting queries, not whole counting queries. So the exponential mechanism, it says, assign a weight to each database, each little database psi, proportional to e to the epsilon over the sensitivity. I'm sorry. E to its utility times epsilon over the sensitivity. Now, to analyze this amazing object, we need the notion of an AlphaNet with respect to the set of queries Q. So we're looking at small databases, whatever small means, and the claim is that every database, so an AlphaNet is a set of small databases that has the property that every arbitrary sized database is alpha close on these fractional queries to some element in the net with respect to this case. So it says that the maximum over all q of q of x minus q of psi is bounded by alpha. And this is true for every database x independent of size. That's an AlphaNet. And the wonderful fact is that for fractional counting queries, there is an AlphaNet of this size. This is the set of universe, the set of database rows, possible database rows. And this is the log of the number of queries divided by alpha squared. This is for an AlphaNet. So that says that the set of all small databases, where small means this size, forms an AlphaNet. So this is the set. This AlphaNet is the set to which we're going to apply the exponential mechanism. When we do it, we take this theorem that we proved here, and we take a corollary where what I've done is I've plugged in this horrible-looking thing for the value v and chugged through the arithmetic. And we use that together with the bound on the size of the AlphaNet. The size of the AlphaNet would be this item up here to conclude 2 alpha beta accuracy for this ugly-looking thing. What is the ugly-looking thing? It basically says that the absolute error is going to be n to the 2/3 at most, n to the 2/3 times this quantity. It's logarithmic in the number of queries. Logarithmic in the number of queries. So if the universe is pretty small, we can ask an exponentially large number of queries. Not 2 to the n, but still exponentially large. That's amazing. And but it also tells us, if we think of the data set as being sort of, each data element is a d-bit long vector. So you've got d attributes. Then this gives us some limits on what we can hope for with this particular technique. If this thing to the 1/3 is as large as n to the 1/3, then we would get an absolute error that was worse than n, and things wouldn't be interesting anymore. So it says that we can handle tons of queries on relatively low dimensional data but the data matrix has to be relatively thin. It can't be square, for example. So there is dimensionality, unfortunately, plays a constraining role for us. What about efficiency? Generating synthetic data can be hard. So here's an example that comes from some joint work in 2009. We have a distribution. We're going to need a distribution on databases. And because, when you talk about computational hardness, you need distributions and families and blah, 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 blah. The general form looks like this. Our distribution is parameterized by a security parameter, and we're going to rely on digital signatures. So here's going to be how the databases are generated. First, we choose a single sign verify key pair from our digital signature scheme. And we're going to create a database where each row is just the message that we're signing for a random message, the signature, and we're going to throw the verification key in there for good measure. So this is what a row looks like in the database. Now, we're going to have one query for each verification key. So the query is going to be, what fraction of the rows in the databases are valid signatures under VK? Now, consider a curator who has a whole bunch of data rows that look like this, but does not know the signing key. And the job of that curator is to come up with synthetic data. So our curator is in trouble. She can choose subsets of rows in the original data set, but she can never come up with a row that isn't in the original data set because she can't forge the signature. So an efficient curator cannot generate a synthetic database that yields approximately correct answers for VK stars for this key without leaking rows that are in the original database. So cryptography plays a role here of telling us about hardness. Now, here's an almost correct intuition, though. Suppose we say, okay, curator, you don't have to release a synthetic database, but release a synopsis that has the same functionality. Now, I'm lying here a little bit, but the almost correct intuition is that that's pretty trivial. You would just publish the key VK star. That's a little problematic, but it's not crazy. So I just want to place that out there for you to see that the synopsis could be easier than creating synthetic data. So how much easier? Well, what do we want from a synopsis? We want to maintain the functionality of the database with respect to our set of queries. So that means that we still want to hide the presence or absence of any individual, but we're going to have now basically the opposite of traitor tracing. And what we're going to be able to show is that traitor tracing implies there are hard to sanitize distributions. And we can show the converse. Now, does anybody here not know what traitor tracing is? Okay, so very briefly, a traitor tracing scheme consists of various little subroutines where the main idea is that you want to hand special decryption keys, one key to each of your paying users. You want to be able to broadcast encrypted content so that your legitimate users can decrypt and get this content. But you want to prevent any subset of the users from reselling the content. So we imagine that the way they resell the content is they get together and they create what we call a pirate decoder. They take the keys that they have and they do something or other, and they get a pirate decoder, which they then sell to other people. And the pirate decoder has the functionality of decoding. Bad for the system. But here's where the traitor tracing comes in. There's a tracing algorithm, and the tracer can ask the pirate decoder to decode a couple of ciphertexts, and it gets back the answer, and based on that, the tracer can accuse correctly at least one person, one of the colluders. That's the general shape of a traitor tracing scheme. So some user in the coalition will be traced, and users who are not in the coalition, who did not collude and who didn't do anything wrong, will never be accused. So for us, we're going to start with a traitor tracing scheme. There's some private key length and some ciphertext lengths. We're going to have one universe element. These are our database rows for each private key. So this is the key that we gave to user 1, this is the key that we give to user 2, and so on. And the query set is going to be what fraction of rows, for what fraction of rows I, is it the case that when we apply the decryption key for user I here to the ciphertext C, we get 1. So if we had a synopsis, something that captured the functionality of this data set, even though it isn't a synthetic data set, what would it mean to capture the functionality? Well, the fraction is going to be either 0 or 1. So the decryption, in other words, it'll just be the decryption of C. And tracing will reveal at least one of the keys, and it never falsely accuses. And so this would violate differential privacy, because we'd have an answer that can show up when a certain key is in the data set with non-zero probability, and have probability of 0 when the user is not in the data set. Now, no one ever talks about this, so we're going to have one slide on the intuition for the converse. If we start with a hard-to-sanitize distribution on databases, and no, I haven't defined it, but I'm just telling you that it means in some strong sense it's going to be difficult to come up with a synopsis that has the right functionality and preserves privacy. So we're going to choose a random database from this distribution. We're going to have a bunch of counting queries, and every user key is just going to be a small subset of the rows of the actual data set. This is a user key. So we know, and this was at the heart of the small DB AlphaNet argument, that almost every small subset of the rows will give you approximately the right functionality. And so we'll use those fractional counts to encrypt bits. And the hardness of sanitization, when we actually get around to defining it, will tell us that it's possible to identify a participant in a coalition-built set-top box. That'll end up happening by definition. So just the most recent results, I think, on this are, or at least some attractive results. The following, assuming secure cryptography exists, differentially private algorithms for the following will require exponential time. First of all, synthetic data for two-way marginals. And this is a much, much more intuitive, natural set of queries than our weird contrived things that involve signatures. And the proof uses digital signatures and PCPs. And if you could do differentially private synopsis release that will handle n-squared arbitrary counting queries, I mean, that also is hard. And that's a result of Ullman. And again, the proof uses traitor tracing schemes. And here's where I'd like to break.
That very theoretical, like pathological cases where...
Oh, I don't think that the two-way marginals is at all pathological.
But assuming that your data is going to be cryptographic, you're trying to provide privacy when you go to provide privacy in data.
So, this is very general. These are very general two-way marginal queries.
It's very tricky to define privacy to only hold for some forms of data and not others, is the problem. So that's a very problematic relaxation to think about.
Okay, here's where I'd like to break.